Best time to buy and sell stock. Have you ever wondered how top engineers spot patterns that lead to big wins? Best time to buy and sell stock is not just a must-know pattern mastery 100 question. It appears in almost every Fong interview loop and stumps over 40% of applicants. Mastering this problem gives you an edge in any technical interview because it teaches you to recognize profit opportunities, optimize for efficiency, and think like a Wall Street pro. Ready to discover the secret? Let's dive in. Let's break down the problem. We're given an array where each element represents the price of a stock on a given day. Our job? Find the maximum profit we can achieve by choosing a single day to buy and a different day in the future to sell. If there's no way to make profit, return 0. No short selling, and you can't sell before you buy. Let's assess our options. A naive brute force solution would check every possible pair of buy and sell days, but that takes O(n)² time, not scalable for big inputs. Instead, can we track the lowest price seen so far and always check the profit if we sold today? This only needs a single pass and O(1) extra space. Super efficient. Remember, always buy before you sell, and update your max profit as you go. Here's the structure of our plan. Start with variables for the minimum price so far, set to infinity, and maximum profit, set to 0. Loop through each price in the array. If the current price is less than the minimum, update the minimum. Otherwise, calculate the profit if we sold today, and update max profit if it's higher.
Let's try to implement it using solution 1. We start by creating a class named solution. This is just a container where our method will live. Think of it as opening a toolbox before picking which tool or function to use. This line defines the function max profit, which takes a list of stock prices. Our goal is to figure out the most money we could make by choosing the best day to buy and the best day to sell. We initialize min price to infinity, basically the largest possible value. This is like saying, I haven't seen any price yet, so assume the highest imaginable price. As we loop, we'll keep updating this with the lowest price we encounter. Next, we set max profit to 0. Since you can't have a negative profit when buying and selling once, we start from 0 and look for something better. Here we begin looping through each price in the list. This loop touches every element once O(n) time complexity. We check whether the current price is lower than the lowest price we've seen so far. If it is, that means we've found a better day to buy. And if the price is lower, we update our min price. In plain terms, this might be the cheapest day so far. Remember it. This operation is constant time O(1). Otherwise, if the price isn't a new minimum, we check whether selling today could give us more profit than any previous day. We calculate the profit by subtracting the lowest price we've seen from today's price. If that profit beats our current max profit, we update it. This line sets max profit to the new, larger profit value. It's like saying, selling today would earn more than any other day so far. Let's update our best result. Finally, we return the highest profit we found after scanning all prices. If the prices kept going down, max profit remains 0, meaning no profitable trade was possible. And that's how this algorithm works. It first sets up trackers for the minimum price and best profit, then scans through prices once to update them whenever a better buy or sell moment appears. Efficient, simple, and elegant. Check. Time to confirm this solution with the classic stock profit test case. Here's the input. Prices equals 7, 1, 5, 3, 6, 4. Each number represents the stock price on a given day, and the goal is to find the maximum profit from buying once and selling once later. Our algorithm tracks the lowest price seen so far and continually checks the best profit achievable if we sold today. Here's what happens. Start with 7. This becomes our initial lowest price. Next comes 1. This is lower, so it becomes the new buy price. Then we see 5. Selling at 5 after buying at 1 gives profit 4. Next 3. Lower than 5 but still above 1. No change to best profit. Then 6. Selling at 6 after buying at 1 gives profit 5 new max. Last 4. Profit would be 3, which is lower than our current best. The highest profit observed is 6 minus 1 equals 5. The output is 5. The expected result is also 5. And everything lines up perfectly, confirming the logic works exactly as intended. Now let's try another implement approach using solution 2. We start by creating a class named solution. This is simply a container where our method will live. Think of it like opening a workspace before adding your tools. This defines our function maxProfit, which takes in a list of stock prices. Our task is to compute the maximum profit we can make through multiple transactions, as long as we buy before we sell. We set up max_cur to track the current running profit. You can think of it like a temporary balance that goes up or resets depending on how the price moves. And here we track max_so_far, which records the highest running profit we've seen at any point. This is the value we'll return at the end. We loop through the prices starting from index 1, comparing each price to the one before it. This loop touches each element once on time complexity. We compute the difference between today's price and yesterday's price. If the price increased, this value is positive. If the price dropped, it's negative. We'll use this daily gain or loss to update our running profit. This line updates the current running profit by adding today's difference. If the result ever becomes negative, we reset it to 0. It's like saying, if the streak of gains is broken, start fresh. This technique is the same idea behind Kadane's algorithm. Here we check if our new running profit is the best we've seen so far. If it is, we update max_so_far. This ensures we always remember the highest profit achievable. Finally, we return the largest running profit accumulated over the whole list. That's our maximum achievable profit. And that's how this algorithm works. It first sets up trackers for the current and best running profit, then scans through each day's price change to accumulate gains while resetting bad streaks. Efficient, simple, and elegant. Check. Let's validate this test case. A scenario where the price keeps dropping. Here's the input. Prices equals 7, 6, 4, 3, 1. Each number is the stock price for the day, and we're looking for the maximum profit from one buy and one sell. Since the price continually decreases, there is no day where selling after buying would yield a profit. Walking through the logic. Start at 7. This is our initial minimum. Move to 6, lower, so update the minimum. Then 4, even lower, update again. Then 3, update. Then 1, update once more. At no point do we encounter a price higher than our current minimum, meaning the algorithm never finds a profitable sell opportunity. So the maximum profit stays 0. The output 0 matches the expected 0, confirming the algorithm correctly handles cases where no profit is possible.
Let's have a quick recap. Breakdown recap. This problem is all about timing your trades for maximum profit. You're given a list of stock prices, each representing a day, and your goal is to find the best day to buy and a later day to sell to achieve the highest possible profit. You can only make one transaction, buy once, sell once, and if no profit is possible, you simply return 0. Assess recap. At first, checking every pair of buy and sell days seems logical but quickly becomes inefficient as the input grows. The smarter approach is to think dynamically, track the lowest price seen so far and calculate potential profits on the fly. This shift from brute force to a single pass solution transforms the problem into an ON time, O1 space optimization, fast, clean, and elegant. Structure recap. Our plan followed a simple logic loop. Keep two variables, one for the minimum price we've seen and one for the maximum profit we've made so far. For each day, decide, is today a new minimum, or could selling today beat our previous best profit? Step by step, the loop narrows down the best buy-sell combination automatically. Implement recap. In practice, we brought this logic to life by simulating the market day by day. Each iteration either updated the lowest price or recalculated potential profit, steadily refining the outcome without needing extra storage or nested loops. The program effectively thought like a trader, balancing opportunity and risk in real time. Check recap. When tested with our sample input, the logic held perfectly. Buy at 1, sell at 6, and lock in a profit of 5. Every step confirmed the reasoning. Quick comparisons, instant updates, and a final result that matched the expected outcome. It's efficient and intuitive once you see it in motion. The biggest takeaway here is pattern recognition, spotting opportunities by tracking key values as they evolve. This problem isn't just about stocks, it's about optimization under constraints. Once you master this logic, you'll see it reappear in countless interview questions that reward smart, efficient thinking.